Now let's refresh our memory on how memory and pointers actually work. To do this, we're going to use an analogy called memory lane, right? So memory lane is a street, and there's a bunch of mailboxes along each street, right? Just like your normal street where you grew up, things like that. And remember that every mailbox has an address. So on this particular street, the addresses start at 000, then they increase by 1 with every house that we go along the street, and all the way up to 6, right? So this on memory lane here, each of these mailboxes represents one location in memory. Every location in memory is a place where we can store things. So we can store a number in each of these mailboxes. So every mailbox has a value, which is what we store in it, and every mailbox has an address, which is its location on the street, or actually in memory, as the case may be. Now, to access this, we have a mailman, right? And this mailman is the part that decodes addresses and names and figures out how to access and how to write to the different mailboxes, right? This is what the role of the computer and the compiler do, right? So if I have a list, the mailman keeps a list of who lives at each address. So if I want to address a letter to Smith, I want to send a letter to Smith, or the variable Smith, the mailman keeps track of what address Smith lives at, which in this case is address 01, right? So when I want to send the value 127 to Smith, I say Smith is equal to 127. The compiler looks up the address for Smith, and then we can copy that value to that particular location in memory, right? And this is how we store values in variables. If I want to do the opposite, if I want to query the value of Smith, I say, I want to add 1 to Smith. So I have to access Smith. The same thing happens. We look up the address, we access that variable, and we get the value from that location. Now this breaks down because in like a mailbox, a real mailbox, when we take a value out of the mailbox, or take a letter out of the mailbox, the value is no longer in the mailbox, right? The letter is no longer in the mailbox. In this case, every time we access it, we're only copying it. Until we write a new value into that location in memory, it's going to stay the same no matter how many times we read it. Same thing. Now, let's talk about pointers. Now, a pointer is just a special kind of mailbox. This particular location in memory, this particular variable, it's still a variable, a pointer is just a variable, but instead of holding a value, the value that it holds is an address to another location in memory, right? So in this case, we've got an evil villain that wants to send spam to everyone, so he's going to use his special pointer mailbox to say, send spam to the mailbox addressed by this pointer, right? So it's his current pointer is currently storing the value 000, and we're going to use that to interpret as send something to that location, right? So we're going to send spam to 000. Same thing happens on the mailman side, except instead of, he doesn't have to decode it by variable name, he only has to decode it by the address itself. So it's a much simpler process for the compiler here. So it's just going to copy that spam to location 000. Now what's handy is instead of having to say, I want to go to location 1, we can just add 1 to the pointer, and now we can access a different memory location. We don't have to access it by name. We can increment a value and then access that location. And this is exactly what we do when we're using array indexes and stuff like that. That's the same sort of thing that's happening. So now I can send spam to location 2 or location 1 without actually knowing the name that's there. And same thing for everybody else on the block. I can just keep sending spam to everybody using this pointer, right? So the thing here to remember is that a variable is a named memory location that stores a value. A variable is a location in memory that stores a value, right? A pointer is a variable, but its value stores its value is an address to a location in memory. So a variable is a name that refers to a location in memory that stores a value. A pointer is a variable that stores an address to another location in memory, right? And that's all it is, right? So arrays are much bigger, and in memory, our real memory lane is billions of bytes long in most cases, right? For your CPU, for the laptop that you're sitting in front of, or something like that, you've got gigabytes, right? Well, that's billions of bytes, and each one of those locations has an address. So memory lane goes off farther than you can possibly imagine. But for embedded systems, it's limited to usually kilobytes. So we've only got thousands of locations in memory rather than billions, right? So what happens with arrays is that array is a name. It's just a variable, but it's a name that refers to a set of locations in memory, a collection of locations in memory where a collection of values are stored, right? So that's a good overview of how arrays fit into this. Now let's look at what they look like laid out in actual memory, right? So here's a memory map. We've got our occupied memory at the top of the block here. We've got our address, which starts out at the top at 0xFF, and we're going to go down in this case, right? So when we have some piece of code like this, we've got int I, and that declares a variable of the type integer that needs to be allocated in memory, and the compiler does this for us. Note that every byte in memory has its own address. So this is byte 1, byte 2, byte 3, byte 4, so on and so forth, all the way down. So every byte has an individual address, and a byte is only 8 bits. So an integer is much bigger than that. It's actually 4 bytes, right? So when we say, I want an integer I, the way it's laid out in memory looks like this. Byte 0 of the value I, the variable I, starts here, then there's byte 1, then there's byte 2, then there's byte 3. So the value I is spread out over memory like this, right? But they're all next to each other. They don't actually spread out in memory and go all over the place. They're just clunked together and cut together in a contiguous block. So they're accessed all at once. Also notice that the address of a variable points to its first byte in memory, right? So if I were to get the address of I, it would be FE rather than FB or something like that. It always would be the very first byte of memory. And when we access it, we're actually telling the computer, give me the 4 bytes starting at FE rather than give me byte 0 of FE, byte 1 of FE, byte 2 of FE, or of I, 3 of I, so on and so forth. We get the 4 bytes starting there and chunked all at once, right? If we want to do something like an array, this does basically the same thing, except it multiplies them by the size of the array. So rather than just one integer, it's going to give me 10 integers, and they're going to be laid out in memory like this. So the 0 byte of the first integer in A starts here, then 1 byte, then 2 byte, then 3 byte, then the first byte of the second integer in RA, then 1, then 2, then 3, then the first byte of the third integer in RA, and so on and so forth, all the way down, right? So this is how an array is laid out in memory. Again, it's arranged contiguously, all in one big block from the start of the array, which is the address of the name. So the address of the variable, if I just said, what's the address of RA, it would point to the very first byte of the very first element in the array, right? So notice that this starts at 0, and what this 0 index actually is an offset, right? So basically when we're accessing an array, we say, give me the third element starting at the address of array, right? Or RA in this case, right? So what it does is it takes the address of RA, multiplies the index by the size of the data type, in this case it's 4 bytes, and then adds it to it. And that gives us our location in memory and allows the system to access it. So let's look at a code example to really drive home how this works. In this particular code example, we're doing a couple of things. We've got an integer I, and we've got a random array of 10 integers, just like we had before previously. I dump a whole bunch of random numbers into that array. Then I spit out randomX just to show you how this works and what this printf does. So this is a formatted print, and it has an LD here. And what this LD means is I'm going to print out a long decimal. It's a 64-bit decimal. And that's what I need to be able to print out the complete address of a particular value on this particular computer. Right. So basically, I'm printing out a big number with these printfs. So I've got my randomX here. I print out the the maximum value there. Then I print out the address. Right. So remember, the name of the variable of an integer, or the name of an array, is its address. So when I print out rand array, I'm not going to print out the value, I'm going to print out the address of rand array. Then I'm going to go through and I'm going to print out the address of every element of rand array, right? So let's see what this looks like. Okay, so here's our code. I'm on Replit, which is a super handy little site that allows us to write code and test it without having to boot up a big IDE and stuff like that. So it goes pretty quick. And I'm just going to hit enter and watch this stuff execute. Right, awesome. So here I've got my randomX, my big value over here. That's the first part that prints out down there. Then I've got the address of the array. So this is some number in memory, and it's going to be different every time I run it. Let's run it again. I've got a different number. It's generally in the same space, but look at the last few numbers. This one is 24864. This time I run it again. Now it's 54992. And this is memory allocated by the operating system that's running wherever this is happening, because it's on the internet, it goes somewhere else, right? So this is the first element of the array, as proven by, I'm doing it down here too, and when I print rand array 0, the address of rand array 0, it's the same thing, right? So here we've proven that rand array, the name, points to the first byte of the first location in memory. Now notice that rand array of 1 also is offset by 4. So there's 4 bytes in an integer. The next value is 4 bytes later in memory. And the same thing here. It rolls over, 4 bytes later, 4 bytes later, 4 bytes later, so on and so forth, all the way down. So here we can actually see how memory is laid out just by looking at the addresses of these things. And this is real, right? Now, the reason why we're doing this is because part of dealing with embedded systems is having complete control over the computer, is having complete control over what the machine is doing and what the machine is what's happening in the machine. And it's important that we focus on and remember how memory is laid out so that we can make sure we don't make any mistakes and don't have anything explode on us when we're controlling important equipment or safety systems or anything like that. So it's really important we keep an eye on how memory is laid out, and we're able to control and manipulate these things very carefully in our designs.